Everybody. So while I'm sort of taking a break from studying for my French final exam, I thought I'd record this quick little video on a neat little trick for integration that I discovered today. And what we're going to be doing is looking at integrals of the form ln of x to some power n times some other function f of x. Sorry. Um, so how are we going to approach this? Um, well, first I want to start off with um, an example, right? So let's take integrating just ln of x dx. Um, you've probably ran into this integral in maybe a second semester sort of upper level calculus course, right? Like second semester still like an introductory calculus class, like a calculus 2 or whatever. You've probably seen this integral as one of the prime examples of where integration by parts comes really handy, right? Because this looks really simple. Natural log of x is really a nice and important function, and we know that the integral of 1 over x is natural log of x, right? So we would expect the integral of natural log of x to also be something simple. And it isn't too complicated, but you just need integration by parts to do it. And so I'll quickly go over the derivation. You essentially say that you have x is your derivation symbol, and ln of x is what you're going to sort of take the derivative of in the new integral. So let's say u equals ln x and v equals x. So du is 1 over x dx, and dv is dx, right? So here we see that we have the integral of u dv. So this is going to be uv, which is x ln x, minus the integral of v du, which is x times 1 over x dx, which is just dx. And of course, this is going to simplify as minus x. And then for good measure, we'll put a plus c, just so people don't get mad at me in the comments. But for the most part, throughout this video, I'm going to be ignoring this just for convenience. Right, so the answer isn't too complicated, but we see this factor of x sort of appearing. And when we check the solution by derivation, we see that when we take a derivative of the x, of course that just goes to 1, and then when we take a derivative of the natural log, we get a 1 over x, which is going to cancel out with the x, right? So we see that that's a sort of nice property here. But now what we're going to do is approach this in a different direction. So let's say I'll let I equal this integral here, ln of x dx. I'm going to call I'm going to define a function I of a to be the integral of x to the a dx. Now, what happens if I take a derivative with respect to a? Right? I is a function of a, so I'll just denote this as I prime of a. But here on the right-hand side, we have variables x and a. So we need to make it clear that we're working with that we're taking a derivative with respect to a, and we're treating x as a constant. So we're going to use a partial derivative notation. So if you haven't seen this before, this is a partial derivative. And what a partial derivative means is you just treat every other variable like a constant, instead of, if you've done implicit differentiation, you sort of have to include these dx, dA factors. Now, this derivative just goes straight inside this integral because the integral is with respect to x. Now, the derivative of x to the a, where a is our, we're taking a derivative with respect to a, so this is going to be ln of x times x of a dx, right? We just get, it's an exponential function, and we multiply it by this extra factor, ln x, right? Think of it as taking the derivative of e to the x. You could say it's ln of e times e to the x, but that ln of e is just 1, right? So we ignore it. So we see this extra ln of x term popping up. But now if we set a equal to 0, this x to the a term is going to become 0, right? Or not 0, but x to the 0 is going to become 1. So the integral becomes ln of x dx, right? So I prime of 0 is I. So what can we do with this information? Well, we could compute I of a explicitly in terms of a, right? We know it's the integral of x to the a dx, and that's a simple power rule. We just get x to the a plus 1 over a plus 1. And of course there's a plus c here, but I'm not going to worry about it because I'm going to take a derivative anyway, right? So we've taken a derivative of this with respect to a, right? Now notice here we have this x to the a plus 1. That's an x to the a times x, and that x is a constant in term with respect to a. So I'm going to take that term out, and then we have x to the a over a plus 1. I want to take a derivative of that, so we're just going to use the quotient rule. We get a plus 1 squared in the bottom. X to the a gives us an x to the a ln x, and then we multiply by a plus 1, subtract, then I take a derivative of a plus 1, that's just going to give us 1, and then we have x to the a. And so I can factor out this x to the a, so we get x to the a plus 1 times, I guess, a plus 1 ln x minus 1 over a plus 1 squared. And then we take that formula and plug in a equals 0. We get x times ln x minus 1 all over 1, right? So this is just x times ln of x minus 1, which is the same thing we got before, right? And that's what we expect, because here we showed that we would expect I prime of 0 to give us the same answer as I, and we just verified that result. So how is this going to help us in obtaining expressions of the form integral of ln of x to the n times f of x? Well, let's first look at the simpler case of ln of x f of x dx. And let's consider, again, the same, I'm going to use the same notation here, and let's consider the same replacement of ln of x by x to the a. Then when we take a derivative with respect to a, once again, f of x is completely in terms of x, and so is dx, and this integral is with respect to x. So this derivative is only going to hit this term, and we are going to get an ln of x factor times x to the a f of x dx, right? And in a no, I can't do that. I almost thought I saw something interesting there, but I can't do that. So what was I thinking? Right? And then once again, once we set a back equal to 0, this x to the a disappears, and we get the original integral ln of x times f of x dx, right? And so the important thing to notice here is that when we take this first derivative, what changes is this factor of ln x. But ln x is a constant with respect to a. So if we were to take a second derivative, I double prime of a, then all we have to do is differentiate this x to the a term again, and that's just going to give us another ln of x term. So I double prime of 0 is equal to the integral of ln x squared f of x dx. So the general methodology here is to replace ln of x by x to the a, integrate that new function, and get something in terms of a, take as many derivatives as you need, and then replace a with 0, right? Now, what am I noticing here? Something interesting that I just noticed. And so one example I wanted to do here, which I haven't gone through with the details yet, but it shouldn't be too bad because I think this is an integral you can do just using integration by parts. I just sort of conjured this up in my head, and I believe that this isn't too bad, right? Because you would differentiate this, you would integrate 1 over 1 plus x squared, and that would give you, let me think. So you'd have ln x arctan x minus. So you'd have to take an integral of arctan x over x. Is that? I don't know. But we can do it using this method, right? So let's say I of a is going to be the integral of x to the a 1 plus x squared. Okay, maybe this isn't as simple as I thought. Yeah, no, I done goofed. Okay, so that's that idea out the window. Let's also think, so something else I notice is these repeated powers all applied at the same position, right? So I of 0 is going to be the integral of f of x dx. So I of a, if we use Taylor series, is going to be I of 0 plus I prime of 0 a plus I double prime of 0 a squared all over 2, and so on, right? And so this is going to be integral f of x dx plus the integral of ln x f of times a plus this also isn't looking to come out as nicely as I thought it would, because you can bring this all inside one integral that you have multiplied by f of x, and you have 1 plus a ln x plus a squared ln a ln x squared over 2. Oh, I see where this is going. I guess I'll keep going with this, just for the heck of it. But if you notice, this inside here is just a power series in terms of a ln x, and this is the power series for e to the x. So this is going to be e to the a ln x dx, and this is just x to the a. I thought I would have gotten something with that too. Guess not. But in the context I saw this problem in, when f of x is a polynomial, especially, this problem is this strategy is super powerful, because you're replacing ln x with another polynomial term, and then you're just integrating a polynomial. You get a bunch of fractions that you take derivatives of, and it becomes really nice. So I thought this would get me somewhere, but it didn't. Oh well. Well, that's it for this video. I hope you enjoyed, and I'm sorry that the latter half of this video is more of just a rant, I guess, or just me trying out things. But hopefully this method brings some inspiration to you, and I'll see you in my next video.